Ever trained a model and watched the loss curve explode to infinity? Or stay flat, refusing to learn anything at all? Frustrating, right? That's exactly what we're going to explore in this video today. Last week, we set up PyTorch, explored tensors, and saw how gradients flow through a model. That gave us a working model. But understanding why a model fails sometimes is where deeper intuition comes from. In this video, we will break models on purpose to see how they learn. We'll start with a minimal training loop, moving data through a model, calculating the loss, and updating parameters. Then we'll peek inside PyTorch modules to see how they track parameters. We'll explore train versus eval modes, use hooks to check activations and gradients, and compare optimizers like gradient descent, Adam, and AdamW. Finally, we'll put it all together and see why the model, optimizer, and gradients work together to make learning happen. This video is about seeing how all the pieces of training fit together, learning from all the mistakes we make on the way, and building intuition that go beyond what textbooks teach. So let's get into it. First, we're going to build a minimal training loop. This is the core of any model training in PyTorch. The loop moves data through the model, calculates the loss, backpropagates gradients, and updates the model's parameters. We're creating a tiny data set where the output is twice as much as the input. This will help us see the training process clearly without any distraction. Here's a linear model with one input and one output. PyTorch automatically creates weights and bias for us. We'll use mean squared error for our loss function, which is standard for regression. The optimizer will adjust the model's parameters using simple gradient descent. Here's our full minimal training loop. We make predictions with model parentheses x. That's the forward pass. We compute how far off our predictions are using the loss function. We zero out the gradients from the previous step. We backpropagate with loss.backward to compute new gradients. And finally, we update the parameters using optimizer.step. This loop repeats for 100 epochs, and you'll see the loss decrease as the model learns. So in this minimal training loop, we've shown the complete flow of data, model, loss, optimizer. You can see every step: forward pass, backward pass, and parameter update. This is the foundation of everything else we'll build on in PyTorch. Now that we've built a minimal training loop, it's a good time to peek inside our model and see how PyTorch manages its parameters. Understanding this will help you know why training works and what can go wrong if parameters are not tracked correctly. Here we define a simple model with one linear layer. PyTorch automatically registers the weights and the bias of this layer. That means when we call model.parameters, PyTorch knows which parameters to update during training. Here we define a simple model with one linear layer. PyTorch automatically registers the weights and the bias of this layer. That means when we call model.parameters, PyTorch knows which parameters to update during training. Notice that in wrong model, we created a layer but didn't assign it to self. PyTorch does not track it. So wrong model.parameter is empty. This means the optimizer won't update the layer and the model won't learn. So the key takeaway here is always assign layers to self in your modules to make sure PyTorch registers them automatically. Optimizers only update registered parameters. If a layer isn't registered, it won't get updated during training, which can silently break your model. Understanding parameter registration helps you debug issues and ensure all your layers are trainable. So in this section, we saw how PyTorch keeps track of parameters automatically, why assigning layers to self is crucial, and how registered parameters connect to optimizers. Next, we will explore train versus eval modes and hooks, which will let us inspect what is happening inside the model during training and evaluation. Now that we understand how models manage parameters, it's important to know that models behave differently during training and evaluation. PyTorch gives us train and eval modes to control this. Understanding these modes will help you see why some layers act differently and why the results change if you forget to switch modes. Here's a model with a dropout layer. Dropout randomly zeros some outputs during training to help prevent overfitting. But during evaluation, we want the full output. So dropout is disabled in eval mode automatically. You can see the difference. In train mode, some outputs are dropped. In eval mode, the output behaves differently. This is crucial when you evaluate your model. You must switch to eval mode to get correct outputs. Hook let us peek inside a model during a forward or backward pass. Here we registered a forward hook on the linear layer to print its activations whenever we run data through it. This is a great way to debug or understand what's happening inside your network. So in this section, we learned the difference between eval and train modes, why it matters for layers like batch norm or dropout, and how to use hooks to inspect gradients or activations. Now it's time to talk about optimizers. Optimizers are what actually update the parameters in a model using the gradients we calculate. Different optimizers behave differently, and choosing the right one can determine how fast or how well your model learns. Stochastic gradient descent, or SGD, is the simplest optimizer. It updates each parameter by moving it a small step in the direction of the negative gradient. It's straightforward, but can be slow to converge on complex problems or when gradients vary a lot. Adam is more advanced. It keeps track of moving averages of past gradients and squared gradients to adjust the learning rate for each parameter automatically. This helps the model converge faster and more reliably, especially on complex tasks. AdamW is a variant of Adam that correctly separates weight decay from the gradient update. This is useful for regularization, helping preventing overfitting in larger models. Now, it's time to put everything together. We'll refactor our training loop into a clean, reusable training structure and see exactly why training works the way it does. Here we wrapped our training loop in a function called train. It makes it easy to reuse different datasets, models, or optimizers. All the key steps are still visible. Forward pass, loss computation, zeroing gradients, backward pass, and of course, parameter update. This structure is much more cleaner and more maintainable. Now let's think about why this actually works. The forward pass computes predictions from the model. The loss function tells us how far off those predictions are. The backward pass calculates gradients that indicate which direction to move each parameter. The optimizer updates these parameters based on the gradients. Together, these components create a feedback loop that gradually improves the model's predictions. Each part relies on the other. Remove any step and the model breaks. When things don't work, here are a few friendly debugging tips. Check your loss. If it isn't decreasing, something is wrong. Inspect your parameters. Are they being updated and adjusted? Verify train versus eval modes if you use layers like dropout or batch norm. Experiment with learning rates or optimizer choices to see how it impacts convergence. Developing this intuition will help you understand training on a deeper level rather than just following a recipe. Okay, so in this final section, we combined everything into a clean, reusable training loop. We explored why gradients, optimizer, and the model work together to make learning possible. By understanding the mechanics and debugging effectively, you can train models with confidence and build intuition that goes beyond textbooks. Thank you, and follow for more.